So, good morning, everyone. Thank you for inviting me once again and having the honor to be the first speaker in the morning. I classified myself being enthusiastic, so I'm here the third time, and I would also address this in the presentation at the very beginning. It's about something track maintenance through the ages, because I have been here 3 times, and I think we can rather good see progress on how we moved on in doing that maintenance for railways. I have to specify, I will talk about track mainly. So there are a lot of different assets, of course, for railway infrastructure. I cannot move forward. Oh, no. In 2017, back in winter tour, I talked about data sources, algorithms, missing data, especially for turnouts, and how we could link all this data-based planning to the actual work on track. And I looked it up. Those days, I said, we are on the way. From today's point, I would say we are well on the way. This happened much faster than expected. How these processes, how this planning idea based on data moved into reality for most of the infrastructure managers, at least that I know. So then it was 4 years later in Zurich. I remember this conference. There were relatively few attendances. I talked about maintenance planning, but also on the maintenance execution, and talked about the idea that the machines on site should also know exactly on site what to do. So on site condition assessment. This was a research project back in those days. And I said it will take years, but it's worth the effort. Today, the first machines are equipped and already operating. So again, faster. So everything is fine. What should I talk about this year to you? Again, 4 years later. First, I would like to start with the current state of the maintenance planning. So I think track data analysis is well developed, both in research, but also with the infrastructure managers. We have really solid measurement data. We achieved the biggest goals. We have them precisely positioned and reproducible. That's always a challenge, but I think this is well done. And also we analyze these measurement signals in very different ways, depending on the focus for different maintenance tasks. When we take as an example the longitudinal level, the track roughness, we could do that using the amplitudes from the raw signal. That would be for single failure tamping, basically something about safety. We could do that as a standard deviation for line tamping, so that we ensure a smooth through-going track quality, keep dynamics low. Or we could also do that wavelength specific with different methods, analyzing rather the ballast quality than the geometry. So we can, and we learned to adjust, to change influence lengths for those different quality indices, with the aim to locate the maintenance demands as good as possible. What are the current challenges in track maintenance? The biggest challenge is we don't know exactly when to do the maintenance. There is most of the time a lack of track closures. We cannot maintain if trains are running, of course. Railways, and you might know that, they have their renaissance. So we have a lot of trains. Fortunately, we have a lot of trains, and we get more of them. So What that means is faster deterioration. We have to do more maintenance. And of course, we also need higher budgets for that. To operate the maintenance and trains, and we expect trains to be punctual. I think, especially in this country, this is nothing what should surprise you. The topic of track closures is critical. So the question is how to establish a maintenance regime having no or not enough time to execute it. What are the consequences? I would say all over the place. In railways, we started to use our tools rather than our knowledge. I told you that before, so we can identify the worst sections with our analysis and keep the quality high with the least maintenance possible. So reduce maintenance and keep quality high. For those relatively small sections to maintain, we can manage that in short track closures, and we can also operate it with quite low budgets. On the short term, this works. And there are many good examples to see different railway networks where this is applied and this works. And our analysis tools helps to operate maintenance in this way. The problem is the long term. Here we definitely run into problems when we plan or think our maintenance in this way. As a first consequence, the unit costs of the maintenance rise. So every single meter that is tamped, that is ground, whatever, gets more expensive. And especially for works where we have a lot of fixed cost, this is more crucial. That means that the maintenance budgets needs to increase faster than the traffic volume. And especially for track renewal, which is not maintenance, I know. But this is very expensive, and then we start to postpone it in order to save money. And the only way to postpone it is to do that by maintenance again. So again, higher budgets. So you see, this is these are a lot of financial issues. The technical consequences occur a little bit later when we start to have or to lose our through-going quality when we only repair failures. So this is something general that is more linked with budgeting, of course, and financing, which is relevant, but probably a bit out of scope in this conference. I would rather go to possible solutions. How could we apply? So when I mentioned first that we use our tools rather than our knowledge, we should probably change that. Not change it, use the knowledge and the tools. So we could use everything that we learned in these more than 20 years on analyzing the condition of different assets or different components to design maintenance in different scenarios built on these evaluation tools. And we can optimize it in very different ways. So we could, for example, choose a scenario where we need to close down the track not that often. I would say this is rather reality today. But we could also try to optimize the intervention level, so maintain a bit earlier to keep quality high. And we could also have the focus to achieve the longest service life possible in maintaining. And if you now would say, okay, this should be the one and only goal of maintenance to ensure the longest service life, most of the time this is not executed. Maintenance is executed on intervention levels, not with the focus on service life. I have tried to bring an example on that, where you could see also the differences between, let's say, something which is long-term and something what is rather short-term. I would do that with temping, so restoring the geometry. We would look at 3 scenarios. So the base case scenario is with the short sections, that's what we apply today. And 2 other scenarios with a bit focus more on quality, scenario 1, more on service life, scenario 2. So when you apply that to the measuring data that we have and change the possibilities or the sections to be maintained, and we look at the different years, and you see this is done for the past because we have the data already and we know the outcome, at least from the basic scenario. The amount of maintenance we need per year is different in this way. That's not astonishing. It's rather that you see also the focus of this work, the section length is increased. Why is this done? In order to keep the maintenance also within the budget, in order to keep these unit costs a bit lower. And probably the most interesting thing is how does the quality over the network develop? And you see this seems to be very similar. So we do different maintenance, very different sections, and quality keeps more or less the same. I would try to summarize that for you. When we look at the amount of temping, so the amount of maintenance which is applied to this example, so it's almost the same. So we are not increasing the maintenance, even though we are increasing the section lengths. That means we shift different sections between each other. The quality is slightly better, not too much, but for those who work with these data, they might know that they're on a network-wide or section-wise basis, this might not change too much. But here is the astonishing thing, the section length is increased very much, so it's doubled. We maintain longer sections in order to keep the network working. There is also a slightly longer service life involved with these 2 second scenarios or 2 alternative scenarios involved. So that could be an option to plan maintenance differently than today, because today it's not our problem to restore quality. Our problem is to finance this maintenance. This might work, but for railways, that would mean maintenance centrally planned and data-based, which is at least the centralized planning not ensured everywhere. And a second topic might help us, and this is more into, would say, research. Even though we have analyzed all those data that we have, and we see deterioration of our assets, of our components, we still act due to that what happens. I would try to explain you this in a very easy example. I would say we look at this standard deviation, which tells us the geometry or the loss of geometric quality of a track. And this looks something like this. So standard deviation increases over time, quite linear. This is very easy for forecasting. This is what we do in standard work. We choose any intervention level I mentioned before. We can change that. And then we go for the maintenance. In this case, tamping. And we do know quite good what happens after tamping. We restore the quality to about the same level we had before. And we can expect a deterioration rate which is about the same than before. It's a bits more, but about the same. So this is what we are used. This is what we take for predictive maintenance. We use our data that we have and do forecasting. The only thing that this process can not ensure is if something changes, of course. So this is a descriptive approach. When the system or something in the system changes, it might not work. And probably the most interesting thing here is we cannot explain why the deterioration happens. We can only handle it. We can describe it. We can forecast it, but we cannot explain why. Therefore, probably to look a bit more into detail, take here, we do not take the standard deviation. We take the raw signal. We have this decreasing quality. And at a certain point of time, this deterioration stops at the poor quality level, but there is not more change. What happens here? This is hard to describe. What is different? There is the same loading, so no external system changes, but deterioration stopped. Then we executed tamping, and we achieved, as I mentioned before, about the same quality, but a much lower deterioration rate. So there must have been something happening in this system. It can only be a certain maintenance job. Looking into the data, what maintenance job was executed, we find a rail grinding action here. So what has rail grinding, so achieving a smooth top of the rail, to do with the geometry in the ballast? And we were not aware that we should consider rail grinding in tamping prediction. If you combine data, you would see that, and we combined it with another measurement data, which is the rail surface. So we're measuring the roughness of the rail, and you see that in this case, the grinding removed the roughness and kept it stable. So we are not talking about the component ballast here. We are talking about the forces. So generating dynamics with rough railheads has a big impact and might be the reason for the deterioration at all. So when we look in analytic approaches that we have, we would find such formulas explaining the dynamic forcings, of course. And you see here the irregularity, and this changes significantly in this example. So we are on the way to find the root cause for the deterioration and change also the maintenance. By the way, rail grinding is much cheaper than track tamping and faster. That might help us in future. So the loading is constant, but the stresses are not. And thinking on that, of course, we know that this is general engineering's knowledge that we talk about dynamics and dynamic forces, of course. But when we go this way from the rail surface to the vehicle response, the dynamics in the vehicle, to the forces of the vehicles and the measured forces in track, we see there is a certain circle that is turning, of course. And this also gives a bit different aspect on track behavior and the maintenance that is involved. Because when we look into detail, every weld of a rail is such a small unevenness in the track. And when you look at the ballast bed, you see there is a link between these failures in the railhead and the ballast deterioration. And then comes the vehicle, takes these dynamics and rolls the the dynamic over the track. So we cannot talk about single failures anymore, or we should rather talk about single failures. It's all single points, and then the track in the end has poor quality. So a combination of what we already have might lead us to those root causes and to a different, a cheaper, a faster, probably a better maintenance. So maintain the root cause, not the symptoms. Yes, in this audience, everybody would say yes, of course, but find the root causes first. That's the issue. In the case of track maintenance, that would be a different approach of maintenance, combining the tamping action with a rail grinding action. We have this already in discussion since years. We call that integrated maintenance. But there is one issue again. This will take longer. And having in mind that we already nowadays have too short track closures to maintain the track, this gives an additional challenge. So we need first to prove that this type of maintenance will generate much less deterioration, so will stretch the time in between the maintenance actions necessary, and therefore in the end will also save track closures and make our trains more punctual. So 1, 2, 3. Plan centrally. And another question occurs, do we have the machines to do that? Our machines probably are designed for a different type of maintenance. And the first topic that I will not talk about, because we will have a second presentation where this topic is in focus, move forward with predictive maintenance for turnouts, because turnouts are crucial. They are safety relevant, they are operational necessary, and they are very expensive. There were not too many people here that joined already 2017. That's okay. So I just mentioned it. This is what I told 2017 as well. So we are on the way. But there was progress. Yeah, okay. So if you question mark that, yes, we did something, but probably not enough in the perspective of turnouts. So when we continuously work on the data analysis that we do, and there is so much in discussion, what do you want to do as research topic with this data? Is everything is done? We can forecast, we can use the data, we already use the data. We still see a lot of potential in finding aspects we have not seen up to now. So we will continue to do that, always with the focus to find the right maintenance. And I'm always struggling with the conference name. But in this case, and for this year, I would interpret the right maintenance would be the intelligent one. And I think the way to move there is one of the key issues to keep our system running, even though we have still more trains, more transport volume, and of course, and probably not more money to do that. So thanks for today.